Hello and welcome to Module 2 in our C language series. Today's session is going to focus on C expressions, but before we get down to that discussion, let's understand the binary system. So how do we convert the number 10 to binary? We take the number divided by 2, take the quotient of this division, divide that by 2. We continue this process until we arrive at quotient 0. Then we take our remainders, line them up in reverse order, place our bases down, and then we take into account the values of just the switches that are on, which means wherever there is a 1 in place. And so here we see we have 2 raised to 3 that's on, 2 raised to 1 that's on. Add the two together, 8 plus 2, and you get back the decimal 10. You can use this process on any number to determine its binary equivalent. Now coming to data types, which form the basis on which we will build our C expressions. So we have character type. We use the term char to define a character type. The size is 8 bits. Why are sizes important? When we're writing C language programs, we need to make optimum use of computer memory, which means we do not use too little, which would result in loss of information, and we do not use too much, which would result in a waste of limited computer memory resources. Therefore, size is important. Coming to integer, we use the term int, as we saw in the last session, to define the integer data type, and the size would depend on the natural word of the host computer. Host computer here being the computer your application will run on. What's the meaning of the term natural word? That's determined by your system configuration. We saw this the last time when we looked at system information, and we saw, for example, on the machine I'm working on, it's an x64 configuration, which means the word size is 8 bytes. Now, having said that, you will see later on when I run a program, the size of integer on the machine I'm working on is 4 bytes. And that's because the size of an integer is not only determined by the word size, but also by the compiler implementation. Now coming to floating point, we have the term float, used to use define floating point data types, and the size would be same as integer. Double floating point would be double the size of float. So if, for example, float is 4, right, which means integer is 4, then double would be 8. Now coming to the void data type, that's more pertaining to functions that are explicitly not going to return any value. Just to conclude, the range and size of integer, floating point and double floating would vary with processor and compiler implementation. And here's another important piece of information. If you're working with Linux, right, with a 64-bit configuration, which means an 8-byte word, the size of a long integer, which we're going to discuss shortly, is going to be 8 bytes. But if we're working with Windows with a similar 64-bit configuration, the size of the long integer would be 4 bytes. Coming now to modifiers, which we can use alongside data types to kind of, you can say, qualify those data types. Let's take first signed versus unsigned. When we talk about a signed data type, what we're saying is that the compiler is going to generate code that will reserve the leftmost bit for the sign. And so a 0 in the leftmost bit would indicate a positive, and a 1 in the leftmost bit would indicate a negative. And this is especially applicable, you can say, to integers, though of course we can have signed character types as well. Coming now to unsigned, there will be no such reservation, which means if there is a 1 in the leftmost bit, the value will be taken to compute the magnitude of the number. Now coming to long versus short, and this is applicable to integers. In case of the long integer, it would be the same size as integer, but the short integer would be half the number of bits of int or long int data type. Now coming to the maximum and minimum values that can be stored in signed and unsigned data types. And we're going to look at the character data type here because that's easier to understand. So here we have 8 bits. The maximum value that can be stored considering an unsigned character would be 255. And that's what I meant when I said that the value in the leftmost bit will be taken into account to compute the magnitude of the number. Now if we talk about signed character types, a 0 in the leftmost bit indicates a positive number, which would mean the maximum value that can be stored in a signed character type would be 127. The minimum value that can be stored would be negative 128. Now to understand this, let's for a minute assume that this is unsigned. If it is unsigned, then the value at this position would be taken into account for computing the number. And so this would be a positive 128. But it's not possible to represent a positive 128 when we're talking about signed character types. And that's because the leftmost bit is reserved for the sign. And so this is going to be negative 128. Now there's a simple formula to find the minimum value. It would be negative 2 raised to the number of bits minus 1. So for a character, it would be 8 minus 1, that's minus 2 raised to 7, that's minus 128. And the maximum value would be 2 raised to 8 minus 1, 7. So that's 2 raised to 7, 128 minus 1, which would be positive 127. Moving on, we're going to look at a program that will show us not only the width in terms of bits that would be held in signed and unsigned characters, integers, etc., but will also show us the maximum and minimum values that can be stored in these. So let's now go to code blocks, and we're going to look at a program called limits.c. All programs in this session are available at a link provided in the description below. You can click on that link to access the code. Right, so here we have a file that we've included called limits.h. So here we have two header files now. We have stdio and limits.h. Limits.h contains what are called macros or constants that define certain values. So for example, we have char bit, which has the value 8, indicating the number of bits in a byte. Then we have char min or sign char min, indicating the minimum value that can be stored in a signed character. We also have the maximum value that can be stored in a signed character, and so on and so forth. You can go through the code. What we're doing here is we're defining the different types as well as an integer without a modifier, and as also float and double without modifiers. Let's run this program now and check the results. So here we have the signed char width is 8 bits, that is, because what we've done in the code is when we're talking about signed char, we've used the size of compile time operator. The size of operator will give us the size of our variable type in bytes. So this is 1 byte multiplied by the constant 8, and therefore we have 8 bits. Now the minimum signed value, as we saw earlier, is negative 128. The maximum is 127. Now you will see the unsigned character width in bits is also 8, but the value is 255. Remember, because the leftmost bit is now not reserved for a sign, which means the value at that position is taken into account to calculate or compute the magnitude of the number. In terms of sign shortened width, it is 16 bits or 2 bytes. And again, we've used the size of operator, which would give us a 2 multiplied by 8, and that's why we have 16. Then we have the minimum value that can be stored in a signed shortened or a shortened integer, and that's negative 32,768. You can use the formulae provided in order to compute these values. Maximum signed shortened value is 32,767. Then we have unsigned shortened, and you can see the width is again 2 bytes or 16 bits. The maximum unsigned shortened value is 65,535 for the same reason that the maximum unsigned char value is 255. The signed in width is 4 bytes, and the minimum value that can be stored in a signed integer is negative 214,748,3648. And the maximum signed value is 214,748,3647. The unsigned int width is again 4 bytes, but you can see the value is much more than what can be stored in the signed integer. And of course, you know why now. Coming next to signed long int, and you can see long integer, as I mentioned, on Windows with 8-byte words or 64-bit configuration is 4 bytes. Right, so the size of integer and long integer are the same. Unsigned long integer is also 4 bytes, but of course that value will be more because, as was mentioned earlier, the leftmost bit is not reserved for a sign. Now you can see just int has a width 4, and that's in bytes, of course, because here we have not used the char bit constant. So if you look at just int, we've just used size of, which gives us the result in bytes. And then we have float, which is 4 bytes, double, which is 8 bytes or 64 bits. So I hope that's clear. Now moving on to how computers represent negative numbers using the binary system. Computers use what is called the 2's complement method to represent negative numbers in the binary system. And why they use the 2's complement method is very nicely detailed in an article on Wikipedia. You can read about it there. But coming now to our example, we have 8 bits here, which is of course a character type. And considering it's unsigned, the value will be positive 128. Now to find the negative of this, what computers do is they reverse all the bits. All ones become zeros and all zeros become ones. They add 1 to this number. Now when we add 1 in binary, 1 plus 1 is 10, which means a 0 is placed here and the 1 carried over. And if we do that, we get this result, which you can see now is negative 128. Okay, so you will see that positive 128 and negative 128 have the same bit combinations, but because the leftmost bit is reserved for the signs, it's going to be negative. Now, another example of using 2's complement. What is this number? There's only one switch that is on. That's 2 raised to 3. That's positive 8. To get negative 8, we reverse the bits and then add 1 to the number. And then, of course, we get our result, which is negative 8. Now, remember, leftmost bit is a sign, which means this is negative 128. Keep that aside, add the rest up. 64 plus 32 plus 16 plus 8 gives us 120. So we have negative 128 plus 120. That will give us -8. Yet another example, this time using 16 bits. So you can see this is positive 32,767 if you do this calculation. That means you add up 2 raised to 0, which is 1 plus 2 plus 4, etc. You will get 32,767. And of course, to find the negative, we reverse the bits and then we add 1 to the number. And now we have 2 raised to 15, which is 32,768. But remember, this is now reserved for the sign, so that's negative 32,768 plus 1, which gives us negative 32,767. Talking about 16 bits unsigned, the value would be 65,535. And so we come back to our formulae which we use. If you have 16 bits, this would be negative 2 raised to 16 minus 1, that's negative 2 raised to 15, which would be minimum value. For maximum, we would use 2 raised to 16 minus 1, and then subtract 1 from that calculation. Coming now to variables again. Remember, we discussed a little about variables last time. We're going to look at how to initialize variables, but before that, declare them using the data types. So we have here int. We saw this last time. We could also have short int, unsigned int. So here we are using the modifier as well along with the data type. The scope of variables could be local or global. Let's look at local variables first. They would be declared inside a function. Local variables are also called automatic variables. A little bit about the term automatic here. It's no longer used. It was used earlier to provide source compatibility with the B language. So you may find it in some documentation, but it's no longer used. Local variables can also be declared inside any code block, not necessarily only a function. Your if statement, as we will learn in the next module, could have a variable defined inside its code block. All local variables will cease to exist once the block has executed, which means all values will be lost, and that's the most important point. Now coming to global variables, what are the advantages? When we have global variables, those values will be available to all functions, and therefore we would use global variables when we want that data to be available to all functions within the program. What are the disadvantages? As mentioned on screen, since we declare global variables at the top of the program, they're going to remain in memory until and unless the program finishes execution, and therefore they're going to take up memory space. Also, because these variables are known to all functions within the program, there's a possibility that one of the functions could accidentally change the value, leading to unwanted side effects. And therefore, it's recommended that we don't have too many global variables. Another reason not to have many global variables is so that our function has its own variables, does its own task, right, and therefore can be reused in another application or another program, right, because it's independent of other functions. Coming now to access type modifiers, and we have two, const and volatile. We're just going to look at a program now to demonstrate const. Const is nothing but short for constant. So here we have in main constant x equal to 100, and we're trying to change the value. When we try to run this program, the compiler throws up an error saying assignment of read-only variable x. When we use the const access modifier, then the compiler will not allow the values to be changed. And therefore, we will use the const access modifier only when we don't want functions to change the value. Right, moving on to volatile. Now let's say we have a global variable G using up memory address 0x0010, and we have the operating system clock routine putting in the time there. Now, of course, this time is going to change every second, but compilers work to optimize certain expressions. What that means is that the compiler will assume that this variable is not changing its value, and therefore would store that variable's value within what is called a temporary register. And I'm not going to go into registers today. We discuss that in a later session. But for now, a register is part of the microprocessor, therefore making compilation speedier, which means that they do not access the memory address every time compilation is done. And so we will not get the correct time. To avoid this happening, we use volatile. Okay, so I hope that's clear. Now coming to storage class specifiers, we have extern, static, register, and auto. We're going to discuss extern and static today. Auto is related to automatic, right? And that's no longer used. As I mentioned earlier, it was more to provide source compatibility with the language B. Register storage class specifiers are for another discussion or another module. So coming now to the extern storage class specifier, when we have large projects in C, C allows us to compile each module separately and then link them, creating one executable file. The question is, where do we declare global variables if we have them? So what we could do is, we could, for example, declare the variables in module 1 and then use the extern storage specifier in the other modules to build associations between module 1 and the variables in these modules. Coming now to static variables. And static variables are of two types. We have static local and static global. What's the difference? Static local will allow for values to be preserved between calls to a function. Static global allows for us to have this variable known only to the file in which it is declared, not to other modules within the application. So to summarize, static local variables are not known outside the function, and static global variables are not known outside the file in which they are defined. And we have a program now, or I should say two programs to demonstrate both of these. So let's first go and see local versus static. So when we have local variables, remember, the values are lost after the code block is executed. So here's our code block. We have an integer unique code. That code is increasing by 34. And every time we call this function, we expect that the unique code will increase by 34. But because this is just a local variable, if we run this now, you will see that both times the value is 34. And you can understand why now, right? Because the first time it runs is 34, yes, but then the value is lost. And so the next time it runs is 34 again. Now we can preserve that value simply by adding static to the declaration of the integer. Now when we run this, you'll see we have 34 and then 68. So I hope you understood the use of static. Now the thing is that whenever we are generating a unique code, we would want to start from somewhere. So let's say we put in 100. We run this now. And we get 134, 168, etc. But is this the most flexible way, taking the user into account? Maybe the user wants to provide their own starting value. So then what do? We would have to declare a global variable which would then be available to all functions, but we're trying to reduce the use of global variables. The solution then is to declare a static global variable, which would then be known only to the file in which it is declared. So now we have static int unique code. You can see that's global, that's at the top. And then, of course, we have a function, right? Series gen. And additionally, we have a value, or rather a variable, whose value is going to be used to initialize this code. So that would be the starting point given by start value. And start value, of course, would be input from the user. You can see we have a printf and a scanf statement there. So after taking in the input from the user, we call series start using start value. And you can see series start is taking that value and not returning any value as such, therefore declared as void, but is just initializing the static global variable. So now we run this program. You can enter the starting point, and then that will be used to generate the code. Right, so I hope you got that. Now moving on. Variable initializations. Very simply, we use a type, variable name equal to constant. Type, variable name equal to constant, integer type initialization, and float type initialization. Constants could be integer constants, float constants, double string, and backslash character constants. Now we've seen one of these in the last session when we talked about the backslash n or the new line character. There are many more. I'm not going to list them out today. We will learn them as we encounter them in code. Coming now to operators, as you can see, there are many operators, but we're going to discuss only up until bitwise operators. Now coming to the assignment operator, that is our simple equal to sign. But with the assignment operator comes a type conversion rule. The value of the right side of the assignment is converted to the type of the left side. What this means is, if for example, if I have a shortened type variable and I'm moving that to a char type variable, I will lose 8 bits. Remember, shortened is 16 bits, char is 8 bits. Long int to shortened, remember long int is 4 bytes, shortened is 2, which means 32 for long int and 16 for shortened. So if we're moving a long integer data type variable to a short integer type, we're going to lose 16 bits. Important note here, conversion of integer to float or float to double does not add any precision. What does this mean? So if I'm moving an integer type variable to a float type, I'm not going to get added decimal places or added precision. Similarly, if I move float to double, remember double gives us more precision. We're not going to get that additional precision. Now let's go and look at a program that demonstrates type conversion. So here we have a char type and then we have a shortened type, both initialized. We are moving now the short int type to character type in this statement. Let's see the result. Run this. The number was 279, yes. But when we move num to ch or shorten to char, the value left is 23. So what's happening here? Let's just understand that. So here we have 279 converted to binary, and of course our code on the left hand side. Now if we lay down the basis and then line up our remainders, right? So we have 2 raised to 8, which is 256, plus 16, plus 4, plus 2, plus 1, which will give us 279. On the left, of course, we just have padding because remember this is 16 bits for the short integer. Now, when we have this statement executed, what's happening is these will be lopped off, as also, of course, the corresponding values. And so we've lost 256 in terms of its value. We're left now with 16 plus 4 is 20, 22 plus 1 is 23. And that's how we got 23. So here's a chart of possible information loss depending on target type. So when we move a char type to a signed char type, if the value is greater than 127, we know we can't represent positive 128 when we have a signed character type, so the target will be negative. When we are moving a short int type to a char type, we will lose the high order bits, or the high order 8 bits, I should say, as we just saw. Similarly, when we move int to char, because int, remember, is 4 bytes, which is 32 bits, and char is 8 bits or 1 byte, we're going to lose 32 minus 8, which is 24 high order bits. Similarly, you move long int to char, you're going to lose high order 24 bits. You move long int to short int, you're going to lose high order 16 bits because long int is 4 bytes or 32 bits, but short int is 16 bits. Then we have moving float to integer. We're going to, of course, lose the fractional part. Remember, when moving double to float and long double to double, we're going to lose precision. Now coming to arithmetic operators, addition, subtraction, multiplication, division. This is modulo, which gives us only the remainder of a division. We're not going to use these today. We're going to look at them in code in the next session. Coming to increment and decrement operators. Now this we need to understand because we're going to use this in code in the next session. So here we have integer x equal to 8. And in this program statement, we are printing out the value of x and then applying the increment operator. Whereas in the next program statement, we are applying the increment operator and then printing out x. Similarly, for decrement, we are printing out the value of x and then applying the decrement operator. And of course, here we are applying the decrement operator before printing out the value of x. So if I run this now, you will see that the value first is 8, then the value is 10. Why? The first time, remember, we're printing out the value of x without incrementing. Incrementing after that. So after this particular statement is executed, the value of x will be 9. Right? So first it prints out 8, adds 1, it becomes 9. In the next statement, we are first adding and then printing out, and therefore we get 10. Similarly, for the decrement operator, the value of x first printed out is 10, then we subtract 1, it makes it 9. In this statement, we are subtracting before printing, and therefore we have the value 8 printed out. Moving on. What are relational operators? We have greater than equal to, less than equal to. This equal to sign is for comparison. So for example, if I say A equal to B, I would use the assignment operator. But if I had to say if A equal to B, then I would use this particular operator. This is for not equal to, again for comparison, if A not equal to B. What are logical operators? These are the logical operators: and, or, and not. And of course, we'll be using these very often in our code. Important to remember that relational and logical operators are based on the idea of true or false. In C, a 0 equals false, and any non-zero equals true. But to understand logical operators, the best way is to look at a truth table. So here we have P is false, Q is false. Therefore, P and Q is false. P or Q is also false. Now this indicates, is P false? Yes, because it's 0, and so it prints 1, which means it prints true. In the next one, P is false, Q is true. P and Q is false. Why? Because both of these need to be true for P and Q to be true. P or Q is true because one of them needs to be true for this condition to be true. Is P false? Yes, it is, and therefore it prints out true. Now P is true and Q is true. So P and Q is true. P or Q is also true. But is P false? No, P is true, right? And therefore it prints out false. And lastly, P is true, Q is false. P and Q is false because both these need to be true if we want this condition to be true. P or Q is true because either of them need to be true for this condition to be true. Is P false? No, P is true, and therefore this prints false. I hope that's clear. Moving on now to bitwise operators. Bitwise operators are used for testing, setting, and shifting the actual bits in a byte or a word, used on char and int data types only. That's important to remember. Now these three, these are the bitwise and, bitwise or, and this is the exclusive or. Again, we'll look at this in a session where we will use them in code. This one is the ones complement. Now you may ask, what is the ones complement? We'll come to that in just a minute. This is our right side bit shift operator, and this is the left side bit shift operator. Or you can call them the bitwise shift operators. So what are the uses of bitwise operators? They can be used, one, for CIPHER routines. What does this mean? We can use this to kind of encode a byte, and then we can use a process to decode it, which I'm coming to shortly. But bitwise operators can be used for CIPHER routines, also for multiplication and division by 2. So let's look at a CIPHER routine first. And CIPHER routines will use a ones complement. Here we have an example. This is the original byte. Now you will notice here that this is just the reverse of these bits. And when we reversed bits earlier, right, when we used 2's complement, the reversal of bits was actually the implementation of 1's complement. And then, of course, this would be to encode. To decode, we would just reverse them again. And therefore, these two are the same, right? So by decoding, we've arrived at the original byte. The first complement encodes, the second decodes. Now coming to multiplication and division of integers with bitwise shift operators. You can see here the first representation in binary is of the number 7. 4 plus 2 is 6. 6 plus 1 is 7. Now we are shifting to the left by 1 using this bitwise shift operator. What happens here is this 0 gets lopped off. The 0 moves here, this one moves here, this moves here, this one moves here. The ones go into place with the last position 0. What's the value now? 8 plus 4, 12. 12 plus 2, 14. In effect, we have multiplied 7 by 2. right? So every bit shift results in a multiplication by 2. Let's take the next example. Shift to the left by 3, which means these 3 zeros go out. Remember, when zeros go out, we are not losing any information. So this 0 comes here, the ones take their place, and then all zeros are put in. The value now is 64 plus 32 is 96. 96 plus 16 is 112. Let's check the multiplication. So taking into account this position, that's from where we're starting. 14 twos are 28. That's the first shift to the left. 28 twos are 56. That's the second shift. 56 twos are 112. Now you know how x shifted to the left by 3 bits gives us 112. That is, of course, starting from 14. Now let's look at the next one. X is shifting to the left by 2. So in the first shift, 1 will move here, and then of course the others will move left as well. But in the second shift, the 1 being here now will move out, which means we will lose some value. The value we will lose will be worth 2 raised to 8, 256. So keep that in mind. This one moves here, this moves here, and then of course all zeros. What's the value now? 128 plus 64, that's 192. We should have had the value 256 plus 128 plus 64. And if you do that calculation, it would be 448. Minus 256 would give us 192. Okay, so that's because we've lost that information. Now shift to the right by 1. That would result in division by 2. So when we move to the right by 1, this 0 gets lopped off. This 0 moves here, this one moves here, this moves here, this moves here. And then the 1 moves here, this 1 moves here, which leaves a 0 in the most significant position. So now we have 192 right here. What is the value now? 64 plus 32, which is 96. And if you divide 192 by 2, you get 96, right? Now we are shifting to the right by 2, which means these 2 zeros are lopped off. Remember, we are not losing any information. This 0 moves here, this moves here, this one moves here. Then the 2 ones, and then of course all zeros, which leaves us with the value 16 plus 8, which is 24. So let's do the division. 96 divided by 2 is 48. 48 divided by 2 is 24. Right? So this ends our session for today. In the next session, we'll be working with program control statements and of course writing quite a bit of code. So till then, take care, stay safe. Bye.